a commercial ferry service operating in one of the world's busiest waterways, carrying passengers at over 150 km per hour, 1 to 3 meters above the surface. Not a concept render, not a Kickstarter, an actual scheduled service, targeting launch in the later part of 2026. And it's been 50 years in the making. This is the Airfish Voyager, and it's the most proven wing and ground effect craft ever built. The crew at ST Engineering AirX, which is a joint venture of ST Engineering and Widget Works, talked to me for One Wingspan Above, and this is the inside scoop. Welcome to a new episode of One Wingspan Above, where we discuss anything to do with ground effect. My name is Paul Dutch. Let's start at the beginning, because this craft's lineage is one of the more interesting stories in the WIG world, and it's one that most people get wrong. The Airfish didn't begin in Singapore, it began in Germany. Hanno Fischer, through his company Fischer Flugmechanik, developed the aerodynamic core of what would become the Airfish series. And a key design decision Fischer made wasn't an aesthetic choice. He chose a platform based on a reverse delta wing, which was invented by German colleague Alexander Lippisch. It was a deliberate engineering commitment to inherent aerodynamic stability. We'll come back to why that matters so much, because it's the foundation that still drives this program today. The design eventually made its way via Flightship Australia to Singapore, where a company called Widget Works took up the IP and built 2 pre-production craft from the initial AF8-001 that was built by Hanno Fischer. These weren't prototypes in the loose sense, they were functional flying machines, and the team at Widget Works spent years actually operating them, tuning the flight envelope, understanding the handling characteristics, and critically accumulating real-world flight hours in real conditions. That's not nothing. That's a competitive moat most WIG startups envy. Then in 2023, ST Engineering entered the picture. ST Engineering is not a small player. This is a global technology, defense and engineering group with a market cap over $25 billion. Its commercial aerospace business is one of the major MRO operators in the world, an Airbus structural component manufacturer, and a leading passenger-to-freighter conversion solution provider. They saw the WIG market opening up, saw Widget Works' proven airframe, and formed a joint venture, ST Engineering AirX. We'll call it AirX for short. All IP has been transferred, and both pre-production craft came along with it. Crucially, so did the institutional knowledge that had been making the Airfish fly for years at Widget Works. It was joining AirX's board. It didn't walk out the door, it stayed with the program. The rebrand to Airfish Voyager reflects a genuine engineering evolution, not just a marketing refresh. The Voyager is a substantially modified machine. More on that shortly. What it gives you is a WIG program with a lineage stretching back decades, real flight data, a classification grade build underway, and one of the world's largest aerospace contractors backing it. In a field full of scale models, renders and roadmaps, that combination is unusual. I want to spend some real time on the physics here, because there's a debate in the WIG community that the AirX team feels quite strongly about. You'll often hear ground effect explained primarily through span ground effect, the idea that flying close to a surface reduces induced drag. And that's real. The wingtip vortices are disrupted, induced drag drops. But here's what AirX pointed out directly to me. Induced drag is only one of 3 drag components. Form and friction drag don't go anywhere just because you're in ground effect. So the total drag reduction you get from span ground effect is often smaller than people claim. And in some geometries, depending on the craft's shape, total drag might not reduce meaningfully at all. The more important phenomenon for a craft like the Airfish is the chord ground effect. This is the direct increase in lift generated by the pressure cushion that builds between a wing of low aspect ratio and the surface beneath it. It's not about drag, it's about lift. The wing generates significantly more lift for the same angle of attack when it's operating in close ground proximity. And that effect is far more dominant for a long chord, low aspect ratio platform than any induced drag reduction. If you want to know more about this, check out our earlier videos that I'll link in the description below. This isn't a fringe view. AirX pointed out that IMO's own guidelines, which defines WIG craft classifications, defines ground effect in exactly these terms. Chord effect. Span effect isn't even mentioned in that definition, and for good reason. Why does this matter practically? Because it shapes the entire wing design. The Airfish uses a reverse delta platform, a Lippisch-derived configuration, which is optimized for chord ground effect. Long chord, low aspect ratio, strong pressure recovery close to the surface. It's not trying to be an efficient glider. It's trying to be an extremely efficient low altitude cruise platform, and that's a fundamentally different optimization. And it leads directly to the other pillar of the Airfish philosophy, inherent stability. The crew at AirX were blunt about this in our conversation. When you're flying at 1 meter above the water, you have no altitude to arrest a failure. If something goes wrong at 9,000 meters in a conventional aircraft, the crew has time. At 1 meter, they don't. So the answer isn't a sophisticated fly-by-wire stabilization system. The answer is to design the craft so that it doesn't want to depart from inherently stable flight in the first place. The reverse delta achieves this. As the craft climbs above its optimal ground effect height, lift drops off naturally, pushing it back down. Pitch stability comes from the geometry, not the software. And that design choice, prioritize inherent aerodynamic stability over active control, is the single biggest philosophical differentiator between the Airfish and some of its more technologically ambitious competitors. The original pre-production Airfish 8 aircraft were a single engine, and that was fine for flight testing, but it created a real limitation operationally, specifically around docking and maneuvering in confined water. The Voyager solves this with a twin-engine layout. The reason is twofold. First, twin engines give the master full differential thrust control, the ability to yaw the craft on the water without needing water rudder authority in tight spaces. The footage AirX shared with me of the pre-production craft maneuvering with differential thrust makes this immediately obvious. Second, twin engines improve the single engine out safety case. In an engine failure scenario, the Voyager can continue to operate on one engine, not in a normal cruise sense, but with enough authority to reach a safe landing area and put the craft down on the water. That's a very different situation from a single engine failure event on a single engine aircraft. I asked specifically about the engine failure certification path. The team confirmed they are conducting tests on the pre-production craft for single engine handling, and the formal validation will be part of the upcoming trials on the classed Voyager. On propulsion philosophy more broadly, yes, the Voyager runs gasoline engines. And I know that raises eyebrows in 2026, but the logic is actually quite sound. The operating environment that AirX is targeting globally, like Batam, Indonesian island resorts, coastal Malaysia, are not infrastructure rich. The principle is simple. If the island has cars, it has gasoline. Charging infrastructure for a high-power marine craft is a completely different proposition, and one that several potential customers told the team they weren't ready for. AirX has also carried out an extensive life cycle analysis of the petrol engine mode compared to other purportedly greener propulsion modes, and found it inconclusive that the latter is better. Even marine-grade electronics in that environment are a significant maintenance burden. Simplicity is an active design choice, not an oversight. That said, hybrid and hydrogen propulsion are on the radar for future variants, just not on the current one, where the weight and power density trade-offs don't yet work in their favour. On materials, the Voyager has made a near-complete transition to carbon fibre composite construction. The pre-production craft were majority carbon fibre even then, with some glass fibre in less critical areas for cost reasons. The Voyager shifts almost entirely to carbon, with one specific exception, where carbon fibre panels interface with metallic structural components. A glass fibre interlayer is used to prevent galvanic corrosion. That's a well understood composite engineering solution for a marine environment. The weight motivation is obvious. This is a craft that flies for a living. Every kilogram saved is payload or range. Control surfaces have also been revised from the pre-production baseline for improved handling based on what the team learned from years of operating PPC-1 and PPC-2. The Airfish Voyager is, from a regulation standpoint, a marine vessel that shapes everything about how operators are trained and certified. The initial framing was what AirX called the Captain Plus concept, a nod to the marine tradition of the ship's captain, but with an additional type qualification for the WIG element. That's since then been refined. The correct designation is now Master, a COC4 maritime qualification, supplemented by a specific type course for the Airfish Voyager, run by AirX. There are two entry paths to this qualification. You can come in through an aviation background or a marine background. Given that the operational environment is firmly in the marine world, marine traffic separation, marine port authorities, marine emergency protocols, the team expects that most operators will come from marine backgrounds, and the training is structured accordingly. The craft is designed for single operator control. The master has full authority over all control surfaces, roll, pitch, elevator, as well as power on both engines. There's no authority sharing between the master and the second officer in normal operations, though a second officer will be present on board for regulation purposes. And on longer routes, they can take over handling duties in the same way a co-pilot rotates on a commercial flight. What struck me about the control discussion is how undramatic it was. The team's position is that once you're staying in ground effect, which you're supposed to do in all times, the craft is simply not difficult to control. The inherent stability does the work. You're not constantly fighting the aircraft. They demonstrated this practically. The team flew a pro-production craft from Malacca down to Singapore, approximately 200 kilometers, single operator, unremarkable. That's a meaningful data point. Key operating parameters for the Voyager as certified. Operating heights, 7 meters maximum with the ground effect envelope. The aerodynamics are still clearly in ground effect at this height. The team confirmed this with analysis. The 7 meter ceiling is chosen primarily to simplify training and keep the craft firmly in the 2D marine traffic paradigm, not because the physics demand it. Takeoff and landing wave height, 1 meter in normal operations up to 1.5 meters in an emergency. IMO requirements for passenger craft necessitate that the craft can land safely in degraded conditions. Crosswind tolerance, 15 knots. Range, up to 500 kilometers. The commercial routes being targeted sit around the 150 kilometer mark, roughly 1 hour's flight, which gives meaningful fuel reserves and operational flexibility. Capacity, up to 10 seats including crew in the Voyager configuration. Safety systems added for the Voyager's class build include additional emergency exits beyond the pre-production baseline, gas detection systems, fire suppression and firewalls around high-risk areas. All of this is being validated under Bureau Veritas clarification rules, alongside the MPA. On the question of assisted takeoff, hydrofoils for example, the team is deliberately not doing it on the Voyager. Their reasoning is careful. Hydrofoils that help takeoff are not automatically benign on landing, and the pivot dynamics of a craft hitting a submerged foil during a water landing needs to be fully understood before integration. They want to get the proven design into commercial service first, then explore assisted systems with actual operational data behind them. The Airfish Voyager is being classified as a Type A wing and ground craft. That's the IMO's destination for craft that operate strictly in ground effect, close to the surface, as opposed to Type B, which can transit to brief out of ground effect flight, or Type C, which is effectively an aircraft. Some earlier coverage, including some of mine, placed the Airfish closer to Type B. The team corrected this directly. The Voyager is explicitly targeting Type A, and its 7-meter operating ceiling is part of that commitment. Fischer's original design intent was always ground effect. Type A is where this craft belongs. Clarification is being handled by Bureau Veritas, and in principle approval for the construction rules has already been received. The Singapore Maritime Port Authority is involved in parallel, working through both the flagging process and their operational permits. The Singapore flag is strategically important. Singapore is an IMO committee member with one of the world's most respected and stringent maritime regulation regimes. Approval there is a meaningful credential in other jurisdictions. The first Voyager built, the fully classed craft, was approximately 70 to 75% complete at the time of my conversation with the team. Marine classification requires inspection and validation at each stage of construction. You can't do retrospective sign-off, so the build process is slow by design. The team is targeting water trials and operational testing in the second half of 2026, with the first commercial charter operations with Batam plans to follow. The first commercial route is Singapore to Batam, subject to regulation approval. That's approximately 40 kilometers of water and a corridor already served by conventional fast ferries, but the Airfish Voyager does it faster and point to point, without being constrained to ferry terminal schedules or large passenger volumes. The commercial partner is Batam Fast, a major established ferry operator running services between Singapore, Batam, Malaysia and Indonesia. Their launch model is charter operations first. The Voyager will operate as a chartered service before transitioning to individual ticket services once regulation permits are fully in place. Singapore was chosen as the launch market deliberately. The team's reasoning: if you can get operational approval in Singapore's congested, highly regulated, mammal protection conscious maritime environment, you can operate almost anywhere. They already began discussions with other maritime authorities, and for instance the New Zealand one noted the specific local requirements around marine mammal speed limits and acoustic impact in harbours. Every jurisdiction has its own wrinkle. I asked directly about how the Voyager sits against something like the Regent Sea Glider's pricing model, where you're looking at ticket prices around the $30 to $40 range. The team's position is they can compete on price, but the variables are complex. Ownership versus lease, flight frequency, route length, passenger volume per day. With a 10-passenger craft, economics work differently than a 100-passenger vessel. Point-to-point flexibility is the value proposition, not volume throughput. The primary target customers for the Voyager in this first phase are resort visitors, time-sensitive business travelers, and small parcel logistic operators. The craft also has an obvious utility in paramilitary, emergency response, and medical evacuation roles, though those aren't the commercial focus. What the Voyager is generally competing against isn't the ferry, it's the helicopter and the seaplane. Both have significant operational constraints in the Southeast Asian environment: airspace complexity, limited landing infrastructure, noise, operating costs. The Voyager sidesteps most of those constraints by living in the marine domain. Beyond Singapore and Batam, the roadmap is ambitious. AirX is actively pursuing Malaysia, multiple routes; Indonesia, resort archipelago operations; debris heavy water that actually favors the no hydrofoil airfish design; Mediterranean, at least one confirmed customer in discussion; South Asia Maldives, already announced; India, flagged as a major future market; Japan, Korea, Caribbean, Pacific Islands, Australia, all identified. New Zealand came up specifically in our conversation, and not just as a polite gesture as I'm living in New Zealand. AirX don't have direct customers in New Zealand and might not be one of the priorities at the moment, but the team has already contacted New Zealand's maritime authorities and received a detailed set of local requirements back. The mammal conservation rules in particular are more specific here than in most jurisdictions, so the interest is real even if the timeline isn't set. I want to say something here that I think is worth putting on the record. The AirX team is generally careful about how they discuss other WIG programs. They decline to criticize competitors by name. Their position, and I think it's the right one, is that the WIG industry needs everyone to succeed right now. If a high-profile program has a serious incident before this technology has established a track record of safety, it sets the whole field back significantly. The team's point about this was blunt. Some days somebody's gonna get killed if the industry relies too heavily on active electronic stabilization systems in an environment where a failure gives you almost no time to recover. And that's not competitive criticism. That's an engineering safety concern that the whole sector needs to hear. The team also made an interesting observation about skinny wings in ground effect craft, and I'll paraphrase here rather than quote directly. The high aspect ratio platforms may be optimizing more for span ground effect efficiency than chord ground effect stability. Given what we discussed earlier about how those two phenomena actually work, you can draw your own conclusions about the implications. I'll leave that here. The Airfish Voyager is not the end of the line, it's the proof of concept for a commercial program. The next major milestone is a larger craft currently in a conceptual study, targeting 24 to 40 passengers. The team is using data from the current pre-production aircraft and will use operational data from the Voyager to inform the configuration choices. Engine type for the larger variant is still generally open. Diesel, hybrid, hydrogen, and gasoline are all being evaluated. And the weight and power density constraints are real constraints rather than excuses. The timeline for a large variant is a test program around 2028 to 2029 with broader market introduction targeted for 2030. Between now and 2030, the plan is to build more Voyagers, get them operating, accumulate the kind of commercial track records that regulators in new jurisdictions will want to see, and progressively expand the operating envelope. ST Engineering composite manufacturing capabilities, they already produce Airbus floor panels and aircraft structural components at scale, give the program a generally credible path to production scaling. This isn't a startup trying to figure out carbon fiber layout for the first time. The industrial capability exists. "50 years from Hanno Fischer's first drawing of the reverse Delta platform to a commercial ferry service in the Strait of Malacca. What strikes me most about the Airfish program is the discipline. 17 years of which it works, operating with a zero marketing budget. Every dollar spent on engineering. 2 pre-production craft that actually flew, thousands of kilometers in actual conditions. An inherent stability philosophy that they haven't compromised even when the temptation to add fancy electronics must have been real. and now ST Engineering's industrial machine behind it, taking a proven design through proper classification for the first time. The WIG world has plenty of ambition. It could use more of this kind of patience. I want to thank the AirX team for their time and their openness. As trials progress and the Voyager gets closer to the water, I'll bring you updates. And if I can find an excuse to go to Singapore while this thing is running, I will. Until then, keep on skimming.